Thank you for the introduction. And I also want to thank Nancy and Matt to invite me be here. It's a great pleasure to be here. Just, as introduced that I supposed to give this talk early this year in the spring. And then that day, suddenly there's like snow and ice, and it got canceled. And then this time I got worried about a hurricane. But it doesn't really affect that much. I'm so glad I'm be here. And I also thank you for coming here, because I was not expecting this large population after this hurricane. So thank you to be here. I'm so glad to visit the campus a second time to share my research related to restoring the motor function in amputee with a smart prosthesis. All right, so I will start to briefly talk about my research lab. So I lead a lab called the Neuromuscular Rehabilitation Engineering Laboratory. So in the lab, our goal is to advance the assistive technology, such as a prosthetics exoskeleton, that could help the person to move, and then so with the essential goal to improve the quality of life for people who have physical disabilities. So we are dealing with the situation we call system is, I would like to use my, the system we're dealing with is very different from just a pure robots or human. We are dealing with the system that partial human, partial robots, right? So the robots and the human has to function together, hand in hand all the time, with the goal to empower the people's physical capability. So how do we do that? So that's our research questions and the science related to this human-robot interaction. So in this talk, I will mainly focus on my research related to prosthetics. So why this is important? The number of individuals with a physical disability in the US is continuing to grow as the population ages. And then just a specific related to people individual has a limb loss. There are about 2 million people that in the US has a limb loss. This is actually a statistic about 10 years ago. So this number is continue growing. The other is these, individuals require assistive device because they lost a limb. Usually this assistive device is prosthetics. All right, I'm listing a couple of prosthetic devices that if you go to a regular clinic, probably you will see folks gonna wear the device like this. So for example, for the upper limb device, there's many patients still using, this is called a passive cable-driven body-powered prosthetic hand. So it has a bicycle cable that is rolling around the shoulder. So basically the person uses a different shoulder motion to operate the hook, open or close. Okay. There are motorized, very simple, just a gripper as a hand. So that is the electrical motor. For lower limb, all these devices I listed are passive, means it doesn't generate power. So the person, in order to walk with this device, they have to use a lot of their own body motion to compensate, because the joint is fixed. It doesn't really, or it's flexible in a certain circumstance, but it doesn't generate power to allow a person to walk. Okay. Well, in the past, I would say 15 years, there's a huge change in the field. So it's an advance of the field, which is great. With the technology of a battery material, as well as those actuators, so generating this motorized advanced prosthesis became available. This is all advanced mechatronic design. So on the top row, on the top, you will see all these are powered, so motorized prosthetic legs. So the knee joint or ankle joint had power. So imagine, this would power you to walk. It's definitely much better compared to those passive devices. These devices allow the person to, like say, climb the stairs, which with a passive device they can't, right? So they can, but they could do only one step at a time. But with this device, they became more walking in a very natural way. And then the bottom row is showing an advanced prosthetic hand, so they became dexterous. Each individual finger could be motorized. Especially this one is called a deck arm that has every finger is motorized, and they have 2-degree freedom wrist, elbow, and then 3-degree freedom powered shoulder joints. So these devices are great, but they haven't really highly adopted by the patients. Why is that? So although the mechatronics is hugely advanced, but how about the control? This device, so for example, I'm showing this example is my student actually control the deck hand. So I show you the deck arm, but in my lab, I only has the hand and the wrist, okay? And then you can see how my student is a control. So actually, this is a commercial device. The control is actually use the foot. See. So you can see she is moving the foot. There's an IMU, it's called inertia sensor, that it will sense the motion. And then if you tilt your foot in a different way, then you can operate the prosthesis. So as you can see, she has to learn, right, which foot would rotate, which foot will open the hand. And it basically she's doing this task, dancing around. Okay, well, is this an option? So it takes a long time for her to learn. And then more importantly is if she starts to walk, she needs to disable this, right? Otherwise the hand is gonna go crazy. So how do we really need to control it? It's based on the person's intent. How do we control our hand? Just think about it. With the intent, you can drive that. So we need this neural interface. I wanted to give you another challenge in the lower limb prosthesis. So first, let's see how exciting of this patient. This is a real patient that who is the first time to fit this powered ankle, so called a biome. And this is a powered, so the ankle joint is motorized. So you can hear what he say.
Actually, it was somebody gave me back my life today. That's kind of simple. After 12 years of being whatever.
So you see that he's so excited. He said, someone give back the leg. First time he could start to use the ankle to walk. But I also want to show you this video that he walked in the real world.
It's not kicking.
The kicking means provide the power during the push-off.
Well, it depends. I mean, you really don't have a choice.
So what happened is, when he walked in a real environment, then things stop to work. Because this device is a kind of a pre-programmed for perfect level ground. When outside the pavement has a slope or on the grass, then device kind of lose that function. So the control is not adaptive to the environment. So I hope I lay out strong reason why we need a better control of this robotic device. So our aim in the research, we are trying to enable seamless integration of human and this robotic smart machine to assist and augment the human's physical capability and performance, and hopefully their experience. So in order to do that, what do we need? Right? We just have to be adapted to all kinds of task contexts in the environment. All these devices need to be personalized because everybody is different. We have to ensure the safety. At the end, we put the embodiment there. So what what the embodiment mean? It means we are hoping, right? So in terms of a bionic limb, is the person use this robotic device no longer as a tool, rather they think this is a part of their body. Just like those science fiction, right? The movie you saw. And then can we do that? How do we do that? So in this talk, so my lab is actually touch upon each individual feature. But in this talk, I will focus on embodiment. So what is important that you feel this arm it became your own? So one is the arm has to really follow what your intent are. The other is probably you want to also sense this arm, just like the prosthetic arm, just like you sense your hand. So I would talk about the neural control. So basically, these devices started to work based on the person's intent. We call neural control. So imagine when you wanted to control your hand, all those neural signals came from the motor cortex in your brain. I'm showing this whole pathway. Okay, this is a human motor control system, the pathway. So usually with your intent, the neural signal came from the cortex, motor cortex. And it travel along your spinal cord, and then the signal will transmit through the peripheral nerve until it hits the muscle. So the signal along this pathway are your neural intent drive, okay? So in this study, in my lab, we extract the neural signal mainly from the muscle, okay? And this signal is called electromyography, EMG in short. So I'm going to first demonstrate some of my research that focus on how we achieve the neural control of a prosthesis using the muscle signal. Prosthetic arm in the upper limb. In the clinic, so EMG control, this myoelectric controlled device is available. It's very simple. It only controls the hook, the hand open close, just one motion, okay, 1 degree freedom. Usually you have one electrode, which is you can put on the surface of the skin to pick up that muscle signal. Usually you put one electrode on the flexor side, and then one electrode, this side is extensor, I'm sorry, and then one on the flexor side. And then each one, so when the extensor activated, then hand open. When this is activated, then hand close. That's it. Okay, so now imagine you also have a rotation, the hand rotation you need to control. In this situation, what are you going to do? So with this control paradigm, there's no way. So what you need to do is you have to co-contract the muscle, so doing a one trick. So the device will know, oh, actually you want to operate you actually want to operate the rotator rather than the hand open close. Then you use this two flexor and extensor to rotate the hand. So in this situation, if you add in another degree freedom, things became non-intuitive. So recently, there's a company, they released a new way they can control. It's basically using the machine learning, right? We talk about the artificial intelligence. So what this does is they put a lot of electrodes surrounding the muscle, at the surface of the residual limb, so pick up the different sides of the muscle signal. And then they let the person to try, attempt to imagine doing hand open or close or rotations, as long as these patterns are different. They're using a pattern recognition technique. As long as there's a muscle pattern showing a difference when you intended to do one task or the other, then they can separate. The machine became smart. Then the machine, once they see this pattern, they say, oh, this is a hand open. Okay? So in this case, the control is follow exactly what you wanted to do. I'm going to give you an example here. This is my student. He wears the electrodes on the forearm, control this rotation. So there's a hook, open, close, and then the rotation. 2 degree freedom. And then on this side, here's a control that's a proportional, like direct control. So the basic clinic way, it's a non-intuitive. And then on this side is using the machine learning approach, pattern recognition. And you can tell the performance. On the left side, you can see you need to do this co-contraction to switch which joint to operate. And then still using this two motion to control. On the right side, basically the hook and the rotator follow what he actually doing. Well, clearly you can see the machine learning AI part win, right? So it's faster. They already got the 4-pin. Okay. All right. So this is wonderful. You know, this advanced AI is definitely helpful based on this example we show. But the challenge, I don't know how many of you are working on maybe AI-related research or maybe a coursework. So one of the challenge for AI is these machines at the beginning, they are not smart. You have to teach them. That means every time when they downing this electrodes, they have to learn. The person have to teach them what type of a pattern means hand open. So there's a training period. We call the machine training this machine. Or we can call this a calibration of the machine. It is quite long, so they have to do all the tasks first. And the machine started to know, oh, this is how it works. This is the pattern I actually started to recognize. The other is this machine learning cannot handle the change. So for example, when your muscle started to get fatigued, or somehow your electrodes get wet, then your signal started to drift. The pattern started to change. This machine is not smart enough to tell the difference. Then they stuck. So when you contract, the machine just don't know what to do or do wrong things. So that's the challenge for using the pattern recognition. I'm showing you, this is the real situation. We have a patient come over to test the task. You know, at the beginning, he would have driven this joint, no problem. But once, you know, after a while, he started to use this for a function task, he just had a hard time to stabilize it. Because of this machine is not reliable enough. Okay, I'll stop here. So what are we going to do? So in my team, we start to think, okay, well, think about how we really, you know, the biological system work. When your muscle was activated by the neural signal, so first is the muscle going to contract. So the electrical signal became a mechanical energy, right? The force became a muscle force. The muscle will pull this joint around the joint so that you can generate a motion. So there are process, right? From the electrical to the mechanical became a motion. So this process, it has a biological process, step by step. What a machine learning is actually doing is, I don't care in the between. I only care when the EMG looks like this, and the output will be that motion. I don't care the force, how you map. Could it be neural network in between, and those parameters make no sense, right? So that's why when machine learning, when you have change of the muscle activity, then it became stuck. So how about remimic this biological process to decode this EMG? So this is exactly what we currently do. So this work is done by Dustin Crouch, now is already in the University of Tennessee, and then Dr. Li Zhipan. So what we come up with is exactly what I just said. Rather than use those machine learning approach, we actually building the decoder following this biological process. So we build a muscular skeletal model. So the EMG as a drive goes through this model, and then it generates a motion. The benefit of that is So if you remember doing the pattern recognition, you can only do one motion at a time, right? So when we work on, let's say, I want to reach out my arm, I move my shoulder, elbow, and the hand and the wrist all together. So, and it's a continuous fluent motion. So this would allow the continuous simultaneous joint coordinated movement. Okay, so I want to quickly just showing what we find. One is this model works. It can predict the joint motion. So I'm going to show you, this is a plot. We are decoding two joints, wrist flexion extension and the hand open close. So we call MCP joint, okay, to represent the hand open close. And you can see the black line is what we measured from able-bodied person, right, trying to move. And the red line is what we predict through this model. So the model really followed this black line really, really well, although not meet the same magnitude all the time, but the prediction is very close. The second one is it's reliable. We let the person to try different posture. So this is the reason we try a posture, because the pattern recognition cannot handle it. If you train your machine here, if you wanted to do the same task here, it doesn't work. So we try different posture. And what do we find out? The green line, the green bar showing the accuracy for meeting this MCP joint. The black line is showing the wrist joint. And then you can see across different posture, the performance is very consistent. So they're reliable. That's another good thing. The third one is the most exciting one, is everybody, right? So although we are different as a human, right? We have different size, but the anatomy is very close. If we build this model based on the anatomy, can we just build one model fits everybody, rather than the pattern recognition you have to train everybody. Once you put the device on, you have to train the machine. So this calibration part could be really quick. Okay, so we did. So we collect a lot of able-bodied person's data and then clump some of them together to build a generic, user-generic model. Okay, well, I know I talked a lot of details, but here I want to show you how it works. So this is the ending results. So it's an able-bodied person, okay, 4 electrodes on the forearm. And then you can see this deck arm would be able to follow this coordinated motion continuously pretty well. We even put this into a functional task. This is, again, we are using the able-bodied person to try this generic model. So this model is basically applied to everybody. Once you came to the lab, you do need to calibrate the maximum muscle contraction to normalize the signal, but otherwise, that's it. You see, it's still pretty challenging for doing the functional task, but in general, yeah, we are also, for this one, we're adding the supination, pronation as well. So there's a 3-degree freedom. Okay. Now the question is, your generic model is built upon able-bodied person. Does it work for amputee? So we did have one amputee came to the lab. So you can see she lost a hand. She has a transradial amputation. We put the electrodes on, and then this is, again, just put it on, let her try a little bit. We didn't put a physical system on her just because we don't know if this is gonna work or not. We first let her to do this simple game. Basically, it's a posture matching. So basically, this bar means showing the hand motions, hand open close, and the wrist flexion extension. And we gave her a target, different target to meet. So she needed to, get to this posture. So it's a posture matching. And see how her perform the first time, she just put it on, practiced a couple of trials, and this is how she does. She would be able to control the 2-degree freedom continuously, no problem. Although there's some jittering, she needed to get used to this. And then remember, she hasn't really used this muscle for controlling the wrist for a long time. And she would be able to do it. So this is so exciting. So our next research is we really wanted to putting this as to putting this into a physical system, let her try different functional tasks. I also wanted to demonstrate, this is again using the 3-degree freedom model to perform pouring of water. Overall, he didn't spill, but you see this whole bottom was squeezed. Although the general structure is still maintained, we are pretty happy, but this is the best we can do. So what happens here? Why we can't, produce this processed grip force? Because the person cannot feel, right? They can't feel what a prosthetic hand feel. So the person using the visual just see, right? Once the bottom became squeezed, okay, I need to stop. So I think the biggest part for the next step is really to restore the sensory. Let the amputee to sense the prosthetic hand. Can we do that? So this is our current ongoing research. I'm not going to talk more detail, but there also have a couple of other groups trying to do this. So it's very, very important to close the loop. So I listed this picture for the putting the ponytail together. Imagine for amputee, they will have a very difficult time to do this because they can't see, they cannot sense. So therefore, they cannot precisely control their hand to do this task. Okay, well, so that's for upper limb, all the hands. So now let's look at the lower limb. In my lab, I also design and study a robotic prosthetic leg, which they are all motorized. So for example, this is the prototype in my lab. It's a motorized knee, so the motion is all powered through the motor. And then the basic control is all autonomous control, means there's no direct connection between human and the machine besides the physical connection, okay? So there's no direct commands. Everything is through this machine sensing and then control. That's it. So autonomous control. It's a very simple control. So it defines what type of gait phase the person is in, and then you adjust the joint behavior in different gait phase, allow the person to walk. All right. So a little bit detail the technique part. We call this state machine. So each 4, 1, 2, 3, 4, that 4 circle, it's represent the one state machine for one task. So for example, you walk on local motion on the level ground, then you have one circle, right? 4 state defined. And then if you have stair ascent, then you have another loop, because you have to control differently when you walk on the stairs compared to walk on the level ground. Does that make sense? All right. So when you have more tasks, like a ramp ascent or stair descent, then you just continue expanding these circles, state machine, in order to do that. So one thing is missing is the transition from task to task. So I'm going to show you one example. The device has no idea. Stop. Okay. Well, let's pause a little bit. So the device has no idea what is in front of the person. The person could walk on level ground and then suddenly came staircase. How does the device know the next step gonna be the stair ascent? So current solution, I'm going to play back this one. The current solution is actually using body motion. So the person either can do a very simple trick, like tap 3 times, that inside of the leg that has a sensor. Once you tap, the sensor know, oh, here you wanted to walk on stairs. For this situation is he needed to do this rocking motion. So putting the center of mass back and forth, so the sensor know, oh, here you wanted to walk on the staircase. I'm going to change the way that I control. And then, oh, no. Here, one more time. So he rocked, and then there's a switch so he can walk on the stairs. And sometimes it failed. So person rocked, but didn't trigger the prosthesis to change. In this case, the knee doesn't bend. He has to go back and do this again. Okay. So I was thinking, okay, this is because a lack of direct communication between the human and the robot device. So how about, again, using these residual muscles to recognize what a person actually wants to do? And usually the muscle contraction is really before you make this transition, right? So you're prepared for it. If you can tell, then this transition can be seamless. So what I did is we make this neural interface, again, using the residual muscle signal. We recognize the task the person wanted to do, the next step, okay? And then we can select appropriate task. All those cyclic movement, right, walking, the cyclic movement is still controlled by autonomous control, so the state machine. Okay. I'm going to skip the detail, but I would just a general idea is we're using not only the EMG, but also some of the motion signal that we can capture from the prosthesis socket, like this IMU. Again, the IMU is, we mentioned the inertia sensor, can capture the motion. And then the loading situation, the signal, all together to predict what the next task the person wanted to do. And then we put this into the control directly, see if the person can translate the task seamlessly. So I'm going to show you our current, this is already test. So both subject is walking towards another terrain, transit, without doing any motion tricks. We just go. And the decoder would be able to tell what the person actually doing and continue driving the device in appropriate state machine. Okay, that circle, choosing the correct circle. So this result showing, we made it work. It does work. The question will be, I only show the best trial, right? As an engineer, we know we will never make a perfect system. There always has error. So if you ask me, do you have like error in the decoder, right? So to predict the person's intent? Yes, absolutely. So if we calculate use an engineering matrix, usually it's 95 to 98% accuracy we can generate. So then I got a question like, oh, so that means if the person walk 100 steps, you're gonna have 5 steps, the person gonna fall. I don't know. Would that happen? So that's a really interesting question, right? So you basically say your engineering matrix is say 95% accuracy. How this really means to the patients clinically. So what we did is, okay, how about we simulate those errors? That's often happened, the error that we often see. And then we just purposely putting in the control and then see what happens. So I'm going to show you 2 videos. So one video shows the arrow effect, nothing. And then the other shows the arrow does affect the person's stability. So I would start with the good one. And then pay attention to the flash of the arrow. Okay, I have like a slow replay. So basically you see nothing. At least visually you can't tell. And then the person also report, say, I feel nothing. I don't feel any weird thing happen. And then the other side, it goes pretty quick. See the flash of arrow? That's the time arrow happens. Can you tell? You see that quick click there? Did you? So actually, none of the arrow really threw the person off. That's great. So they didn't fall. But the second arrow, the person report say, I feel something, and I feel this is unstable, right? So if the person feel unstable, then they would not use this device. Actually, we don't want this to happen. So how do we dealing with this arrow? As an engineer, we're trying to solve the problem. This is what I'm trying to do now. So I just get a grant to focus on how do we design the prosthesis to handle this critical error. So not all the error is critical. So for those error, it's not a big deal. We can relax. We don't have to worry about it. But for the error that's gonna cause a person feel unstable, we need to prevent, eliminate completely. So I'm going to skip this slide, but this is demonstrating we are working towards that. Okay, well, so after doing this work, I was feeling like, great, I solved another problem. The person can transit seamlessly on different terrain. But then I hired a postdoc. She's always giving me a hard time. Great questions. She said, so you allow the person to walk, transit the terrain, which is great. How about the person wanted to jump? How about the person wanted to play tennis? How about the person wanted to dance? So all this autonomous control, right, this circle, is describe a well-studied behavior, which is locomotion. But when you talk about, right, balance, anticipatory balance control, right, posture control, or freestyle dance to engage the prosthetic side, to do that, can you do it? Well, clearly my control would not work, right? I can't pre-program everything in the life. So perhaps the direct Emg control is the way. So therefore, she came to my lab, I'm so glad, and then we started to work on this concept. So think about this Emg, right? The neural signal came all the way to the muscle, activated, and the muscle contract, and then you can move the ankle. When you lost this, how about we make an artificial ankle? Okay, it's driven by the pneumatic muscle. So this black, look at this black lines, is actually called a pneumatic muscle. It's a very, it functions, so it's sometimes called artificial muscle. So this is, once you put the air into this tube, so it's actually a tube, once you put the air in, this tube will shortening, just like a muscle. When you activate the muscle will shortening, generate a force, pulling around the joints to generate a motion, okay? And then we use Emg directly modulating how much air goes into this muscle, so modulating the force. So basically, you think about this Emg. Here is the muscle replace the TA, the tibia anterior, so basically for dorsiflexion. And then the back black line, this actuator is replace gastrus, okay? And then the Emg is to activate this directly. So this is the person that I hired, Stephanie Huang. So now she's a research assistant professor in the lab. So what she does is, so first thing is that we needed to come up with a task. So what type of task? How about anticipatory control? Usually for amputee, they wear a passive prosthesis. You know, when you throw a ball to them, or maybe ask them to pick up really heavy box, yes, they can do it, but they have to use a very bad posture, a lot of compensation from their sound side to do it, okay? They can't engage their ankle. Ankle is important for the balance control. They can't engage their prosthetic ankle. But now, if you give them a power to control, can you do this? So we come up with, so I have an animation here, is we let the person to do an anticipatory control. Usually, when I presented to you engineer, especially mechanical engineer, they were like, yeah, our autonomous control would work. You don't need this neural control. So I said, really? How about the task became the person standing on very narrow bar to balance himself? Still, those engineers will say, oh, we just put extra sensors. We still can do this autonomously. Then I said, how about you throw a very heavy ball to the person? Unless you put a computer vision, okay, camera to see, oh, there's something coming. And you also have to predict how heavy is this thing. Then you can do autonomous control. Otherwise, you really rely on the human, right? Because we have an anticipatory control system. Once we see this, we tense up our ankle. We be able to, prepare ahead of the time. So all these make our Emg control reasonable. So we just did this pilot study during the summer. So I'm glad I'm presenting here. Otherwise, I won't present this. I want to show you a couple of videos. We're still processing the data. So one is this person standing on a 2x4 and then trying to balance, moving this ankle. So look at his ankle. Doing the fine adjustment. For amputee, be able to control their prosthetic ankle in a such way, I have never seen so far. This is using the muscle activity to drive those pneumatic. You can hear the sound of pneumatic muscle, the air pump. And I also want to show you his reaction for pickup. This is a 10-pound medicine ball, a 10 pound. And usually he has to basically lean on his sound side and then do this. So see the performance.
This one goes.
You ready, Steph?
Yeah. Look at the ankle. So the ankle joint. He's really controlling.
That was awesome. Oh my gracious, man. The power in this thing is awesome. I'm having to control it, right?
To not throw you back.
Right, and not come up faster than the intact side. I had to control it, literally, to say, okay, not so much.
This is the first time he tried this for this task. He was so excited because he would never be able to really control his ankle, prosthetic ankle, to do this task.
Let me do it again.
So I'm going to stop here, and I'm going to show you by just showing the posture. On this side, you can see this is using the passive device. Okay, so he can't control. The ankle is fixed. It's just a fixed ankle there. And you can see the posture, how much he actually using his back. I pull out from the website showing the appropriate way for weightlifting or inappropriate way. So this is the exact posture he actually using. He used a lot of back muscles as well as the intact side to balance himself. And then look at the way he actually using the Emg control, the prosthetic ankle. Much better posture, and be able to, using the ankle, totally engage the prosthetic side. So, all right. Well, what is the future, right? I'm presenting, we are still processing this data. It's very exciting. This is one case study, take us a month to finish, but it's really exciting. So what is the future we need to tackle? One is, can we have a better interface to pick up the neural signal, such as, right, even for muscle, because we use a surface electrodes. Surface electrodes are usually easy to be disturbed by motions, the impedance, like you sweating, then the signal became to drift. So can we have a better way to pick up those signals? And then also, we show for the lower limb, we do need autonomous control, right? Especially for those locomotion, walking, because we don't really use a lot of voluntary, right? We don't think about how we walk. The walk, a lot of cases is involuntary, or came from the spinal cord. But we also need the task like weight lifting, all those spontaneous, really intent-driven type of the task. So how do we combine? Where are the limits? Can human really control this prosthetic device, directly use the muscle activity? So to build this reconnection. And hopefully this will altogether bring this embodiment into the person. They really like their device, psychologically wanted to accept this device as a part of the body. Okay, well, at the end, I wanted to say, all this work, I did not do these experiments. Everything is done by students and the postdocs. And then we also, this is our routine. We have a postdoc working on a hip axle, who we are thinking this could be useful for efficient, lifting or powering the people doing a lot of physical work. And in sometimes, where to go? It doesn't work. Okay, but anyway, we also have a student working on, where's my mouse? The mouse gone as well. So we also have, all right, but anyway. So we also have a student work on a really smart machine, use reinforced learning. So can the machine identify what the person's physical capability, right? Or the person maybe wear a backpack, then we automatically empower, generate more power to allow the person to walk more efficiently. So those require artificial intelligence within the controller. Can we do that? And if we put the artificial intelligence into the prosthetic leg, is that safe? All those questions has to be answered. But anyway, this again, what I want to say is, students make everything happen. It's really not just my work or my thoughts. And then at the end, I wanted to thank my funding agency and also the patients, the participants. They are fabulous. They put in their time working with us so that our research can progress. And then we also have many collaborators, clinical collaborators, who help us to do this research. And then with that, I want to thank you for your attention.